In this final tutorial, we're going to take a look at studying sequences using a computer. And sequences really kind of map onto a really nice area of programming called recursion, all right? Which again, mathematically, that corresponds to proof by induction. So all this kind of mixes together in a neat way. The short version of this video is that when you define a function, you can use the function itself to define the function, all right? Let's go take a look at what that means. Okay, so this is a mathematical problem that we've seen before, or a type of mathematical problem that I'm sure we've seen before. If you're given a sequence, let me just close that tab. If you're given a sequence defined in this particular way, you see that the sequence is actually defined as a function of itself, okay? And this is enough to be able to define all the terms in the sequence because every single one maps to the previous one up until the first one. So you always work your way down, and then on the first one, you know it is this particular number k, whatever k is, all right? And so we're going to go ahead and write some computer code that allows us to do that. So I'm going to create a new notebook, call it sequences. And the first thing I'm going to do is write down a Python function that emulates this behavior, all right? So we're going to write def as before, and then I'm going to call it generate a. We called it generate ak. We called it generate a. And this takes two values, the value of n and the k value, okay? And here we write the doc string. So this generates the sequence defined by A0 equals A0, A1. I think it's A1. A1 equals K, and A n plus 1 is equal to 2an minus 7. 2an minus 7. Okay, so then I'm just writing what it does. So if we come back to it, we know. And now I'm going to write the code. So we start off with if n is equal to 1, then I just want you to return the k value and end there. As soon as a function hits the return, it ends. And then otherwise, I want you to return, and now I'm essentially going to write exactly this. So I'm going to write it's 2 times the function itself, okay? 2 times generate a, where n is actually n minus 1, and the k value is the same k value, all right? And so we can just check. I've defined that. Let's make sure it's there. If we generate a, yep, it's all there, and the help function is there. And now we can use it. So if we go generate where n is equal to 1 and k value is equal to 3, for example, generate. So that's telling me I wrote generate and saying I don't know what generate is because indeed we've called the function generate underscore a. If we run that, we get 3. And if we put 2 in, we'd get 6, which would indeed be the right number that we have, okay? Oh, no, actually, no, it wouldn't it? It's missing a minus 7 here, which we're just seeing, which is good. That's better. Okay, now, the question saying, write down an expression for a2 in terms of k. So that's not what I'm doing, right? I'm getting it for one particular value of k. So what we need to do is go to our faithful friend SymPy and create k to be the symbol k. And then if we go generate a, n equals 2, k value equals k, then we get that that's 2k minus 7, all right? Which indeed matched up with the previous one. So that's the answer to that question. Show that a3 is equal to 4k minus 21. With a computer, that's very easy. This wouldn't obviously count as an actual proof of this. But if we do that, we get 4k minus 21. So that's just confirming that works, okay? And then we're getting, given that the sum of the a's, where r is our dummy variable, from 1 to 4 is 43, find the value of k. All right, so we're going to get sum of values. Or let me just make sure I use the same variables that I'm using in in here. Sum of first four terms. That's a good name for a variable. So we'll use the same name. Sum of first four terms is equal to the sum of generate A, and n is going to be equal to r, and the k value is going to be equal to the symbol k for r in range. And remember, it starts at 1 and it goes to 4, so we write 5 there. And then if we go sum of first four terms, we get that, 15k minus 77. And then we can again go back to our old friend SymPy and go create an equation, sim.equation. The left-hand side is going to be the sum of the first four terms, and the right-hand side is going to be, is it 43? Yep, 43. And then we solve that using solve set as a function of k. So we get k would be 8. And we can double check this. If I take the sum of first four terms, but instead of k value being k, I'm just going to put the number 8 in, we get 43 as expected. It's quite a short tutorial, nice one to finish off this section of the book and the course on. If you look at the how-to section, it's really just how do you define a function as a function of itself. And just keep in mind, in the same way that we do when we write a sequence, that what we need is we define something. Oh, why am I using that? Hold on. We need to define something, and when we do, we need to make sure we have some sort of base case, and otherwise some sort of recursion that kind of will eventually get back to this base case. And that's really all recursion is in programming, and it's just having a function where you have it inside, or you define it as a function of itself, which is something that we do in mathematics all the time. Let's go ahead and work through the tutorial, work through the how-to section. There's exercises and solution as well as further information if you want it. There's interesting further information here because we look at timing experiments and how fast recursion versus other approaches can be. So you might find that interesting. And once you've done that, we've completed the first part of the book, which allows us to use Python to tackle a number of problems. What we'll start seeing next is kind of more fundamentally how we build up these tools ourselves if we need them.